Thank you, Roland, David, right, and Birgit for the invitation and the possibility to be here. I found a little bit strange with this. Can you hear me well? Okay, thank you. So today I'm going to present some ongoing work near to be finished, right, with one of my former master students, now a PhD at Université Paris-Saclay. Let me try to present the problem. It's going to take some time, maybe 10, 15 minutes. And then I will talk about what we proved for this problem. So first of all, the first thing I would like to mention is that the setting of our problem is, or the background, let's say, is young mean fields propagating in a sort of black hole, right? But before going to the black hole dynamics, I would like to mention what is, let me check if, oh, I don't know. Okay, let me check that what is known for the case of the Minkowski background, right? Where I think that most of the situation is already very well known, right? If you consider the young mean fields, later I will explain a little bit what is the young mean fields in this case. There are several results in the trying to describe the long time dynamics of this field just in the Minkowski space-time, right? So if you start from initial smooth data, then you consider only 4 plus 1, 1 plus 3 dimensions, right? In 4 dimensions. Then you are smooth for all times, and you have decay to see as time tends to infinity. These are, let's say, all results from the 80s. Then you have a conservation of regularity in a very general setting if your manifold is globally hyperbolic, right? And it turns out that if you change the signature or the metric to something that is, let's say, more complex, then you may have interesting situations. So let me mention this result by Bizon, Rosworowski, and Senginulu, where they consider the Schwarzschild background. And this is probably one of the most interesting situations for us because stationary solutions, let's say the equivalent to solitons, will be important for the long time dynamics. So, okay, so let me go to the background I want to mention here, which is a sort of very special black hole, the black hole called the Reissner-Nordström black hole, which is written here in red, right? This is a standard metric for this special black hole, which represents or is a sort of exact solution for the Einstein-Maxwell equations. You have two particular quantities that are important here, which are the mass, represented here in this constant Rs, and as a charge, Q, represented here. And this solution, you know, is sort of important in physics, right? But probably it's not present in nature. But anyways, it should be present in nature, yeah? However, what is important for us is the fact that you can sort of complete the square here, and the way you complete the square here is a sort of, let's say, extremal black hole, right? When you take some particular values of the mass m, and the charge should be square root of m in order to complete the square, and then you get this extremal Reissner-Nordström black hole. Okay. So the black hole in blue will be the object we will consider here. Okay, it's a very special kind of black hole, and it turns out that it can be written in terms of a sort of special theory called the Belinsky-Sakharov theory. That is something that I'm not going to talk here, but that is interesting because in some sense you can embed this theory in integrable dynamics, integrable in the setting of Jonas' talk, okay? So please remind, this is the black hole we are going to consider here. It has only one particular parameter, m. And you can change variables, renormalize time, right? And the radial variable, you know, you have a sort of horizon characterized by the capital M letter, and you can renormalize the radius, right? Make it embedded in the real line, and then you can perform a conformal transformation of the metric, which is written here, and then you end up with this particular metric, okay? That tells you that essentially your geometry is characterized by two asymptotically flat ends when x tends to infinity, okay? Without law of generality, the time tau will be t, okay? It makes no big difference, okay? So what is important here is that, well, before going to Yang-Mills again, what is important here is the fact that there is a sort of conformal invariance in this matrix, in the case of Yang-Mills dynamics. So instead of considering the very complicated first metric, actually we are going to consider just this one. Okay, once again, coming back to Yang-Mills. Why is important to study Yang-Mills? Well, I think that the most important reason to understand these theories is coming from the fact that they are present in the standard model of particle physics, okay? Or fundamental particles, okay? So Yang-Mills is a non-abelian gauge theory, right? Essentially placed in the special unitary group SUN. And well, you can do more general things for sure, but in nature and in the standard model, essentially is constructed on the basis of these groups, okay? SU3 times SU2 times U1. That's one of the sectors of the standard model. There are other mixed variables, right? Like the Higgs field, but essentially you have a big sector in the standard model where you have a Yang-Mills theory. It turns out that there are recent results in this area. I will mention some of them, but I'm missing a lot of them for sure. The energy critical case is when you consider 1 plus 4 dimensions, for instance, in the hyperbolic setting. And then you have important results in this direction by Xinjin Oh and Daniel Tataru. But let's say physics is in 1 plus 3 dimensions. Yeah, don't say that to string theory physics. Okay. You can also consider the energy critical equivariant reduction of the Yang-Mills model, still in 1 plus 4 dimensions. So you end up with a model with a radial variable in 1 plus 1D, if you wish. let me, I'm gonna write the model here because at some point it will be important for us. So you have the wave operator. Okay. So here you have an explicit solution called, let's say, the soliton or the kink, or as physicists say, the instanton. Okay, it's an explicit solution of this model. You have a stable blow-up mechanism around this this solution, and some unstable behavior also as well. So the stable blow-up mechanism was found by Raphael and Rodniansky, and before that, the unstable blow-up was constructed by Krieger-Schlachtatero. So here's our main setting. So I will follow a very influential paper by Bizon and Kahl, where they considered the Young-Mills field, an SU2 Young-Mills field, placed on the exterior of an extremal Reissner-Nordström black hole. Okay, and remember that the metric we are going to use is the metric G, and the reason is that this is taken from Bizon and Kahl, right? The interplay between the conformal structure of the extremal black hole, right, and the conformal invariance of the Young-Mills equation may lead to the interesting behavior of solutions. So you have two ingredients that are good, right? Spoiler alert, you will have interesting behavior, okay? So the gauge potential, you know, takes values in a Lie algebra, right, SU2, okay? And you have some complex generators, so these are 2 by 2 matrices with complex values following this algebra, okay? For us, it will not be really important, at least in this particular setting, but you have to take in mind that if you want to generalize this to a sort of non-radial, let's say non-radial setting, then you have to follow this algebra, okay? In terms of the Young-Mills field, so you have the Fu mu nu, the classical, and the Lagrangian writes down this way. So here you see the particular setting we are working with, okay, with the black hole. And what is the conformal structure? Here the conformal structure is the following. In 4 dimensions, this term here is just a metric term. It's invariant under conformal transformation. So as I told you before, you can choose a particular setting for your metric because if you solve the problem for one metric, essentially, in some sense, you're solving the problem for any conformally related metric. So we are going to take the metric G, as I told you before. And what is really, really interesting is that Bizon and Kahl proposed a particularly symmetric, spherically symmetric, purely magnetic ansatz, which is written here. So recall that this guy is complex value. But the main representative of this vector potential is a real scalar field called bar phi here, and no one else, only this guy. Okay, so the problem reduces to the understanding of the field bar phi. Okay. So if you enter this, if you plug these ansatz in the Lagrangian, what you get at the end is this beautiful, let's say, result, okay? Except that you have some, I don't know, let's say, inhomogeneous weights, right, in your Lagrangian. And then you compute the Euler-Lagrange equation for this Lagrangian, and you get this. Okay. And now you immediately see that your problem is placed in an inhomogeneous setting because of this letter Q, representing actually the standard KdV soliton profile. It's written here. And additionally, you have this term here, Q squared, and essentially the Higgs potential. Okay. So I recall you that this is an hyperbolic setting, so you can apply this crucial Chatat result from 97, where you can say that if you start out with initial data that is smooth enough, then you continue smooth enough for all times. Okay. Additionally, you have a conserved energy, which is written here, which follows from this continuity equation. However, because of the weights present in the equation, the momentum is no longer conserved. Or if you wish, if we haven't been able to find a quantity representing the momentum that is conserved. But this should be the natural momentum for the equation, just coming from physical intuition, okay? But it's not conserved. Okay, this is also coming from Bizon and Kahl. Let's find the time-independent solution of the problem, right? So essentially, you have to solve this problem after expanding these two derivatives. And what is really interesting here is the fact that you have the classical solution H0 equals 1, plus or minus 1, both are solutions, okay? Those are the minimal energy states. But you have a countable family of a smooth finite energy solution, Hn, and different from 0. And the characterization of this solution is given as follows. So I advance you that H1 is explicit, is the hyperbolic tangent. H2 is also explicit. They were found by Bizon and Kahl. Okay. So Hn has n zeros. So there is a one-to-one correspondence between n and the zeros of Hn. Additionally, all the Hn are bounded by 1 in absolute value, and the limit is 1 or minus 1. Okay. Hn is even if n is even. Hn is odd if n is odd. And finally, the pointwise limit of Hn when n tends to infinity is 0. So there is no better way to represent what I'm saying with a picture. So I stole the picture from Bizon and Kahl. I'm very sorry, Piotr. It's written here. So, Piotr called Wn the solutions. I will call it Hn because you know Kink people. So this is H1, right? Just this one, and you can see that if n is even, then the solution is even. Okay. And if n is odd, the solution is odd. And very importantly, W3 has 3 zeros, and W2 has 2 zeros. This is something I'm gonna mention later. Additionally, Bizon and Kahl provide evidence that Ln, the linearized operator around the kink, Hn, has exactly n negative eigenvalue. So the larger the n, the more complicated is the linearized dynamics. They also introduced hyperboloidal formulation, which is written here in terms of a variable s. There is another variable called u and b, but I will not use them. And a final variable called z, okay, which is just the kink h1, right? And in these variables, you can write down the equation using this variable, and then in some sense, you get a compactification of a space, and then you can prove that you have a decreasing energy in these variables. So additionally, they perform numerical computation to find the quasi-normal modes for H1 and H1, which are written here, okay? And additionally, argue that for generic data, right, H0 is essentially one of the global attractors. So what we are going to try to do here is we're gonna follow one of the key ideas that Bizon and Kahl introduced in their paper, right? Which is the following. There is a sort of change of variables in the problem given by this alpha of x. Alpha minus 1 is the inverse, but it's not explicit. Okay, it is a function with logarithm growth, and then the soliton can be composed with this alpha minus 1, and that's going to be called tilde q, and tilde h will be the kink, right? The principal kink h with this change of variable alpha minus 1. So recall that Q is exponentially decreasing, H is exponentially converging to 1 or minus 1 at infinity. But when you compose with this alpha minus 1, what you get is only 1 over x decay for Q tilde and 1 over x decay for H tilde plus or minus 1, okay? So in some sense, you change your exponentially decaying behavior to polynomial decay. And what is beautiful is the fact that when you compose your solution bar phi with this alpha minus 1, you end up with this PDE, right? A wave PDE. So you get the wave operator, right? And the nonlinear part is multiplied by Q tilde squared. If you remember that Q tilde decays like 1 over x, then Q tilde squared is like 1 over x squared. So in some sense, except by this guy is a dynamic that is similar to Yang-Mills, okay? And the kink solution, remember that we are not considering this problem around 0. We are considering this problem around the kink. The kink solution is H tilde. So it's a kink that it differs from the classical kink. So you may compare this problem with the classical phi-4 model, which is written here. I will say more about this problem in a while. The kink solution is just this guy. For us, the kink solution will be H tilde. Okay. So we start out with a black hole and we finish with a kink solution. So that's what I wanted to say to you. There is a huge literature in kinks dynamics now. So I will try to mention what is known about kinks, but probably I will miss some people in the while. Let's start with a foundational result by Sofer and Weinstein, right? Not directly related to kink dynamics, but at the end it is related. The orbital stability of kinks was studied in the 80s by Henri Perez and Brzezinski. Cucagna considered the phi4 kink in 3D, right? And proved for the first time asymptotic stability using vector field methods. And then Kopylova and Komek, in a series of papers, proved asymptotic stability for scalar field models with, let's say, a sort of degenerate weight or degenerate nonlinearities. And then in 2017, with Kowalski and Martel, we considered the phi4 kink under odd data. We prove asymptotic stability in that case. And some years ago, Delort and Mahmoudi, they provide a detailed asymptotic stability in the case of odd perturbations up to times of order epsilon to the power minus 4. And epsilon power minus 4 is, epsilon here is the size of the perturbation, okay? So as some of you asked in the previous lecture, this is a sort of local asymptotic stability, and this is a sort of, let's say, full asymptotic stability. Some years ago with Kowalski Martel and Han van den Bosch, we provided a sufficient condition to get full local asymptotic stability, for kinks in general, for general nonlinearities, right? Except by phi4 and sine Gordon, okay? And recently, Kowalski and Martel revisited this result, and they succeed to provide a proof that does not use any kind of numerical computation, and they consider it not only phi4 but also phi8 and other models. Okay, that was generalized by Cucagna and Maeda. So actually, this is only one part of the field, right? Phi4 or kinks is only one part of a big field considering asymptotic stability. As Jonas mentioned in the previous lecture, there is a different way to see the kink problems, either by considering as a, let's say, soliton problem with a kink, or trying to consider the problem as a nonlinear Klein-Gordon model with variable coefficients. But you can also do the same thing for Schrödinger, or, I mean, even before trying to understand kinks, people were trying to understand solitons in nonlinear Schrödinger, and so on. So let me just finish with kinks. Phi4 is also very related to sine Gordon, where you can say more things since sine Gordon is a special model. You can prove asymptotic stability even if you have a threshold resonance. In the case of odd perturbation, these are resolved by Jonas and Willem. With Alejo and Palacios, we know that the sine Gordon kink is not asymptotically stable in the energy space, but even though we try to find what is the good space in the energy space, or the good subspace in the energy space where you have asymptotic stability. You can also use inverse scattering transform, and you get more than asymptotic stability of kinks. You can use Backlund transformations, right? And weighted estimate to prove asymptotic stability. And very recently with Maulen, we consider the 4-order phi4 kink, and we prove asymptotic stability of that kink. So, you know, there is a sort of huge amount of people working on this now. What happens if your model has variable coefficients? I think that one person working in this problem for many years is Snelson. First of all, he proved asymptotic stability for all perturbation of the stationary kink in if you have variable coefficients, right? And then he considered near to constant solution in variable coefficient scalar field equations with Alamari. And recently, he proved linear orbital stability for solitary waves in variable coefficient scalar field equations. So we found out that probably the setting for our problem maybe is not yet considered in the literature, what makes things interesting, right? So coming back to our problem, of course, we are interested in the long time evolution and asymptotic stability of the kink H tilde. But one interesting feature of the problem is that, as I told you before, you have an inhomogeneous medium. Unfortunately, our paper with Kowalski, Martel, and Van den Bosch is a general paper, but it does not apply to this setting. We don't have shift, we don't have scaling or Lorentzian transformation, right? Lorentz transformation. So it's a different setting. Kinks, the kink H tilde, it has a polynomial tail. Actually, in this paper, at some point, very late in the paper, we considered some models in the physics literature with, and we avoided the case of polynomial tail because we couldn't treat them. So in this paper, actually, it was one of the first moments we tried to consider the case with kinks of kinks with polynomial tails. One important thing of this problem is that H1 times L2 is not the energy space. So the L infinity norm of the perturbation is not small in principle. Nonlinear terms will be, these terms here will be as large as linear terms. And the spectral theory should be done as well. So I don't know how much time do I have. Okay, 6 minutes. So even though you have, if you consider the kink, the general kink, you have an energy for your problem. And you have a natural energy space where you can plus your perturbations, either, I mean, this term in L2, this term in L2, and this guy in L2, right? And then you can define a particular a subset of the energy space given by a perturbation of the kink solution. And here, the norm that we choose is motivated by the energy. You consider the full L2 norm of the derivative, the full L2 norm of the time derivative, but you have no longer L2 control on the perturbation, but instead a weighted control in L2. So remember, this guy will be important in what follows. And so here's our main theorem. Assume that you have a global solution with this particular setting, right? Your solution is always close to the kink in this particular norm that I mentioned before, okay? Then for any compact interval, here we get right of weights, actually. You have full convergence in locally in space, sorry, to the kink solution as time tends to infinity. So that's our main result, which means that essentially if you have a globally defined solution with this particular control, right? Let's say that is an orbital stability control, then you have local asymptotic stability for this. So actually you can construct a manifold. Global existence is not the problem. The problem is to get this control, right? So we can construct a manifold where this happens, okay? That's the most, I mean, it's not the most important part, I think, because it is somehow a standard in the literature. What is not a standard is that this implies this. Okay, so just some remarks on the proof. First of all, the linearized operator around the kink H tilde is follows an unstable setting. What do I mean by unstable setting? The linearized operator is just this guy with a potential B, and the potential B, you know, for X very large, this guy is small, so you get something essentially positive, decaying like 1 over X squared. But around 0, this guy is large, bigger than 1, then this guy is negative. So you have an essential spectrum starting from 0, but you have a negative eigenvalue, lambda 0, written as minus mu 0 squared. One nice thing of this eigenvalue is that the eigenfunction is exponentially decreasing. You say, okay, thank you for the gift. Yeah, everything is polynomially convergent, but the eigenvalue is not, okay? It's exponentially decreasing. So that's nice. And something that is interesting is that L, this operator, is bounded below by another operator called L tilde, which is just this guy. And both L and L tilde are related. They appear in the energy. But L tilde is in some sense the worst case. Okay, the worst case where we have H tilde as the kernel of this operator, but also is an odd resonance. So it's a very bad setting. Okay, but fortunately, sometimes you can work with L, and sometimes you need L tilde to say, okay, you can go no longer below this part. Additionally, if you follow the Kowalski-Martel myself a structure of the problem, so you should decompose perturbation of the Kink solution with an unstable part coming from phi naught, right? And another part that is orthogonal to phi naught, and the same for U2, okay? Actually, U2 is a very good variable. It makes no problem during the whole paper, right? The big problem is always U1. We will choose U1 orthogonal to phi naught. That's the standard choice. But as I told you before, the energy only gives you this control. And if you have this control, then you only get L infinity control on this quantity, which means that this guy may be growing in X, but not too much, okay? So if you multiply by this 1 over X to the power 1/2, it should be controlled, okay? Anyways, if you have this orthogonality condition, then the linearized operator around the kink is controlled by below by this quantity, okay? And if you have global system, then all these quantities are controlled except by the L2 norm of U1. You don't have control, but L2 log is okay. Okay, so this is the only technical slide of the talk. For people working in asymptotic stability, this is a standard. These are the weights that you use for computing virial estimates. So you have a weight. I only write this just to mention that everything here should be composed with alpha minus 1. You know, you have a particular weight that is exponentially decreasing with a particular decay rate capital A, another with a particular rate of decay capital B, and then you construct your virial weights using these particular choices, okay? And then you consider another one. And what is important for us is that we have a certain decay scale given by capital B that is very large. but capital A is even larger, okay? So here is our first result. This is called the first virial that you want to get for your problem. You use the weight bar phi A, okay? And then you define a variable W1 and W2 given by this multiplication, right? And remember that delta is the size of the perturbation. So if capital A is of the size of delta to the power minus 1/4, then you can say that this virial term here, its evolution is given by this quantity. And what is important here is that with respect to previous results, we are able to get some positivity here, but with a local weight. And finally, we get a, let's say, a small term here that is bothering us, okay? So in order to get rid of this term and get full control on the variable W1, what you have to do is to transform the problem or use a Darboux transformation for the problem. But the only problem here is that H tilde is not explicit. Phi naught is not explicit. Mu zero, the eigenvalue, is not explicit. So actually everything is not explicit. Okay, so what you have to do is to transform the problem to another problem with an operator L naught, with a potential V naught. We can graph the potential V naught. And after some work, right, we can prove that this potential V naught is positive and repulsive, okay? So it satisfies, in some sense, the ideas of our paper with Kowalczyk, Martel, and Van den Bosch. And we can say that the dynamics of the transform problem is very good, right? It's good enough. So this is the second result. After some, let's say, operators that are needed to justify the computations, because you get some derivatives and so on, and introducing another virial functional with a particular weight and a localized variable set and a particular choice of B, right? Then you get the good control on the problem. So this quantity is the one that is going to converge to zero as time tends to infinity, the variable set, which is a localized version of V1, which is a localized version of U1, okay? And then you have some positive guys that are bad guys for sure, but they are small in some sense. So you can get rid of them by combining the two virial identities. So that's the idea of the proof, okay? So thank you for your attention.